So in the past couple of classes, we've talked about linear growth and exponential growth, and we even talked about logistic growth in sort of a general way without learning the formulas, as three possible ways that populations can grow. But not all populations follow a linear or an exponential or even a logistic growth model. There are other growth models, and we're going to talk about one more today. So in your groups, to introduce you to this growth model, I'm going to have you work on this little activity called Bees and Trees of Bees. So this is the science that you need to know to understand the activity. So female bees, which are the worker bees, develop from fertilized larvae, while male bees develop from unfertilized larvae. So as a consequence, a female bee has two parents, a male and a female. And a male bee has only one parent, just the female bee, because the larva was unfertilized. Okay, so this diagram traces the family tree of a male bee back 3 generations. So this male bee, it had just a single parent, one female bee was its parent. And then this female bee, you know, the mother of the initial male bee, had two parents, a male and a female, right? And this female had two parents, a male and a female. And then we go back another generation and we say, okay, this male bee, it just had one parent, a female. This female bee had two parents, a male and a female. So if we were to go back one more generation, I'll do one more with you and then I'll let you finish. This female bee had how many parents? 2. Females have two parents, a female and a male. And then this male just had a single parent, the female bee. And then this female had a female and a male parent. So if you count the number of bees in each generation, in this initial generation, we had just a single male, one bee, right? Go back a generation and look at its parents. It just had the one parent, so there's one bee in that generation. Go back one more generation and you have 1, 2 bees. One more generation, you have 1, 2, 3 bees. Go back one more generation and you've got 1, 2, 3, 4, 5 bees. So go back 3 more generations down to generation 8, counting the number of bees. And then look through the questions for C, D, and E and try to answer them. Yeah. Okay, so let's fill this out. The total number of bees in generation 6, what do you come up with? 8. And how about in generation 7? 13, and generation 8? 21. Okay. And then for the number of male bees in generation 1, I've got 1. And then in generation 2, there are none. There's just the one female bee. And in generation 3, there's 1 male. And in generation 4, there's 1 male. Generation 5, there are 2. And then how many were there in generation 6? 3. And then 5. And then 8. Oh.
So why, I don't understand why, maybe this is just a great part, like generation 1 being male.
Yeah.
How is generation 2 female?
So this is an upside down family tree. So the female is the parent, right? So usually when you draw family trees, like you put the children underneath. Yeah. So this is upside down. We're like going backwards in time. Oh, okay. Yeah. Is that clearer? Okay. So this is this male bee, this female that I put underneath it, that's the parent. Okay. Yeah.
Now you said that and
It's okay. Okay, so if we know the total number of bees and we know the number of male bees, you could just subtract to get the number of female bees, right? Or you could count them up in your list. So in this first generation, there are 0 female bees. And then 2 generations back, there is 1 female bee. And then there's 1 in generation 3, 2 in generation 4, and 3 in generation 5. And then we're going to have 5, 8, 13. All right, so look at these columns that we've filled in. Any patterns jumping out at you? Yeah, Emma? Right, and that kind of makes sense scientifically, right? Because it was the female. Oh, no, never mind. I was thinking about it wrong. So in any generation, however many female bees you have, the next generation, that's how many males you're going to have. It's a good pattern, yeah.
There's also, if you start at generation 4, and then if you look across the generation, start at generation.
Uh-huh.
Yeah, 4, go from 2 to 3, goes up 1, go down, generation 5.
Yeah. Oh, yeah, yeah.
3 to 5 is 2, 5 to 8 is 3.
Oh, yeah, and that's the list, right? Like, so we have the total bees, the list is 1, 1, 2, 3, 5, 8. Yeah, and so you see that same list showing up vertically in the male bee. If you start right here, you get 1, 1, 2, 3, 5, 8. Female bees, if you start here, you get 1, 1, 2, 3, 5, 8, 13. And you also can read it horizontally, yeah. So we would have 1, 1. No, that's not good. 1, 1, 2, 3, 3, 5. Yeah. Yeah. I get it. 3, 5, 5, 5, 8, 8, 13. So you're getting consecutive numbers when you read across from the same list. Yeah. If you just look at the list for total number of bees, what would you predict would come next for generation 9? 34. How do you get that? Add the 7th generation to the 8th generation. Each generation is the sum of the 2 before it, right? So if you look, starting at the top of the total number of bees list, 1 and 1 is 2. 1 and 2 is 3. 2 and 3 is 5. 3 and 5 is 8. 5 and 8 is 13. Yep. So we would predict that generation 9 would be 34. And generation 10 would be 21 plus 34, which is 55. And that same pattern holds in the other 2 columns for male and female bees. We start with different numbers, right? For total bees, you start with 1 and 1. For male bees, you start with 1 and 0, but this adding thing still works because 1 plus 0 is 1, 0 plus 1 is 1, and then 1 plus 1 is 2, 1 plus 2 is 3, and the adding thing still works. Same with the number of female bees. 0 and 1 is 1, 0 and 1 is 1, 1 and 1 is 2, 1 and 2 is 3, and then it falls into the same list of numbers. All right, so if I was going to explain this pattern in plain English, I would say any generation is the sum of the 2 generations before it. You could not. Why? Because a sum is an answer to an addition problem. A product is a answer to what kind of problem? Multiplication. Yeah. Yeah, so you could not say product because that would indicate multiplying the 2 numbers before it. That's a good question. All right, so if I was going to write, so here I have the pattern described in plain English. Now I want to write it using this notation that we've been developing. And I'm going to call this sequence F, right? So we'll call this question F. And I want to write a formula for F sub n, right? How many bees are there in the nth generation? So in English, I would say it's the sum of the 2 generations before it. So what generation would come 1 before the nth? F sub n minus 1. And I have to add to that 1 generation before that, right? F sub n minus 2. Great. We haven't used that. We haven't needed to go back further than 1 writing a recursive rule before, but you certainly can, right? This says that any generation, the nth generation, is always equal to the generation before it plus the generation before that. This is called the Fibonacci sequence. And then you have to give the 2, because you need 2 seeds to start this one, because you need to know the 2 numbers before it. So we would call F1 1 and F2 also 1. You got to give the first 2 numbers so that you can use the recursive rule. This is called the Fibonacci sequence. And it'll be written again. So just to remind you, a sequence of numbers is just an ordered list of numbers. In the B problem, we have this ordered list, 1, 1, 2, 3, 5, 8, 13, and we call this list the Fibonacci numbers. We use the same shorthand that we've been using for sequences for the past 3 classes to talk about any number in the list. So we denote the sequence F sub n. So F1 is 1, F2 is 1, F3 is 2, F4 is 3. So the subscripts give the address, right? And then according to our answers from the B activity, F9 was 34, yeah. 34, and F10 was 55. And what would F11 be? 89, 34 plus 55. Yeah. So a recursive formula for the Fibonacci numbers. So we just wrote it down, we'll do it again. F sub n, the nth Fibonacci number, is equal to the number right before it in the list, which would be F sub n minus 1, plus the number 2 before it in the list, or right before n minus 1 would be n minus 2. Okay, so sub n minus 2. There's our recursive rule for the Fibonacci sequence. The 2 starting numbers, F1, which is 1, and F2, which is 1, those are called seeds. You need 2 numbers to start with in order to start applying this rule. So that's why we call them seeds, because it grows into the whole big list. There's also an explicit formula for the Fibonacci numbers. It's called Benet's formula, but it's so unwieldy that we're not going to even get into it. It's got all square roots and exponents and fractions. Not going to bother with it. Sometimes, just so you know, if you're using my math lab and you do like a help me solve this, sometimes it will use this formula, Benet's formula, to answer the question when that's unnecessary. So a lot of people, when you do help me solve this, that might make it more confusing. If you see Benet's formula, ignore it. You know, ask somebody else for help. All right, so if you know that F39 is 63,245,986 and F40 is 102,334,155, could you find F sub 41? How? Just add them. Yep. F41 is just equal to the 2 numbers right before it. So F40 plus F39. I would just add them together. And I need a calculator because those are big numbers. Okay, tell me what it is. Oh. Okay, so 632,459,86 plus 102,334,155. Okay, so I have 1,655,80141. Okay, 165,580,141. All right, what if I wanted to know what F38 was? Could I figure out what F38 is? Subtract them, yeah. So I would subtract, and if it's not clear to you why you would subtract, right, I would do F40 minus F39, and that should give me F38, because F38 plus F39, right? Any 2 Fibonacci numbers added together should give you the next number in the list, F40. So if you want F38, subtract F39 from both sides. All right, so if I want to do this subtraction, 102, 334, 155 minus 632, 459, 86. We get 390,88169. 39,088,169. So to go forwards in the list, add the previous two numbers. To go backwards in the list, you can subtract consecutive numbers. So who is Fibonacci? His real name was Leonardo of Pisa. Fibonacci actually means son of Bonacci, and his father was nicknamed Bonacci, which means good-natured. So his father directed a trading post in Africa, and Leonardo traveled there, and he learned about Arabic numerals. So Arabic numerals are our numerals, the numbers that we use, right? And prior to that, Europe was using Roman numerals. Okay, so Leonardo learned about Arabic numerals. He thought that they were, oh, like, wow, these are so great. This is so much easier than Roman numerals. And he did a lot to introduce Arabic numerals to Europe. And doing simple arithmetic with Roman numerals can be pretty awful. It's really messy and difficult. And doing an addition with Roman numerals in a base 10 system, way easier. But so this is one of his biggest contributions was just spreading this knowledge to Europe. But the work that he's most known for, and the one that contains this list of numbers that we found from the B problem, was a book he wrote called Liber Abaci, written in 1202. And it had this problem in it that was phrased not in terms of bees, but in terms of rabbits. And it says, a certain man put a pair of rabbits in a place surrounded on all sides by a wall. How many pairs of rabbits can be produced from that pair in 1 year if we suppose that every month each pair creates a new pair from which the second month on becomes productive? I know, the language is old, right? But this says you start with 2 rabbits, you put them in an enclosed space, right? When they're 2 months old, they reach maturity and then they can reproduce, right? So for the first month, we consider they're babies, they can't reproduce. And then from 2 months old on, they can reproduce, and they are going to reproduce monthly.
You mean in their second month, rather than
Yes. Yeah. So it takes them 1 month to mature. Then they just start popping out babies, a pair every month. And the original pair continues to have babies every month. And we're not going to assume any rabbits die in this year. And then those babies take a month to mature, and then they start having babies every month.
And then the first original.
Okay, I'm going to show you a little video sequence that is going to make this clearer and shows that this sequence of numbers is important to this rabbit problem.